Alright, silly people, here's the situation. We have a couple of wave functions, psi n and psi m, which both independently solve the Schrodinger equation in some potential v, where psi n has energy En and psi m has energy Em. Um, and En is greater than Em. That's the problem setup. And we're going to use these Schrodinger equations to do a bunch of funky stuff. Um, First of all, by multiplying the top equation by psi m and multiplying the bottom equation by psi n. Um, so top equation is now looking like psi m over, oh my god, over 2m del squared psi n del x squared plus v psi n psi m equals En psi n psi m. And then this equation on the bottom now has a psi n here. That's still over 2m. And it's del squared psi m del x squared plus v psi m psi n equals Em psi m psi n. Right. What's nice is that the potential term, the v psi n psi m thing, is in both of these equations. So let's use the first one to solve for that. We'll get v psi n psi m equals En psi n psi m plus h bar squared. There's supposed to be a squared here. Psi m over 2m del squared psi n del x squared. And then we plug this into the second equation, which is now looking a little long, but it's fine because now we have En psi m plus h bar squared psi m over 2m del squared psi n del x squared equals Em psi m psi n. Okay, I'm going to group this together in a way that's going to be more suggestive by taking all the stuff which is proportional to minus h bar squared over 2m. And then here we'll have psi n times del squared psi m del x squared minus psi m del squared psi n del x squared. And that is going to be equal to just Em minus En psi m psi n, right? We're going to move the minus h bar squared over 2m to the other side of the equation and realize that the stuff in the brackets is just a invocation of the product rule for derivatives of this particular function here, del psi m del x minus psi m del psi n del x, right? And then this is now looking like 2m over h bar squared En minus Em psi m psi n. For part B, we're given a little bit more information that psi m has two adjacent nodes, x2 and x1, and nodes being points where psi m is 0. And so what we want to do is we want to integrate the entire equation with respect to x from x1 to x2. So on the left-hand side, it's just a little bit of fundamental theorem of calculus. And so we'll end up with the stuff that's in the parentheses just evaluated from x1 to x2. On the right-hand side, the only thing which depends on x is the wave functions themselves, so we'll integrate those from x1 to x2. Psi m psi n dx. And now we have the right-hand side in the form we want already. We just have to evaluate the endpoints on the left-hand side. So we have psi n x2 times the derivative of psi m with respect to x evaluated at x2. And then if you plug in x2 for psi m in here, you're going to get 0 because it's a node. So we ignore that term. We get minus psi n x1 del psi m del x evaluated at x1. And then again, you get 0 for the other endpoint term. So you can indeed write the derivative terms as psi m prime x2 and psi m prime x1, and then you have the result for part B. Right there. Part C is a bit subtler. So we have the information that psi 1, okay, we have the information that x1 and x2 are adjacent nodes of psi m, right? So if they're adjacent nodes, we'll draw a little wave packet here, where it crosses the x-axis at 2 different points that are adjacent to each other. So this is psi m here, and this is x1. This is x2. This is just a cartoon, but it illustrates the fact that while psi 2 is crossing the x-axis at x1, it has a positive slope, and while it's crossing at x2, it has a negative slope, right? What the values of the slopes don't matter that much to us. We do care for the fact that they have opposing signs. And then we introduce a new assumption that there aren't any nodes for psi n in between x1 and x2. So that's assuming that the psi n is just going to sail right over x1 and x2 and never cross 0 for that bit. So that is going to give us the fact that psi n x2 and psi n of x1 share a sign. So they're both same sign, right? That's a lot of information, but it's useful for us. So since we know that psi m of x1 and x2 are opposite signs, we can define them as constants just for fun. We'll define psi m prime x2 as a positive constant a, or it doesn't have to be positive, but then psi m prime x1 as minus b, with the definition that a and b share a sign. And now we can write the left-hand side of this equation up here as psi n x2 a plus b psi n x1. And now the whole left-hand side is just some kind of positive constant or negative constant, depending on the sign of psi n of x2. The point being, it's definitely not 0. It's some kind of value, right? But then on the right-hand side, we're going to do some weird shit. So instead of writing it out, let's start doing an integration by parts on it. So we're going to do u equals psi m, and du equals psi m prime, going with the notation. Uh, we'll have dv, we're choosing psi n for that, and then v will be the integral from x1 to x2 of psi n. And since we know that it's not crossing 0 in that interval, we can also define this as some constant. So I'm going to define it as a constant c, but it's going to end up not mattering all that much. So now the right-hand side, carrying out the integration by parts, we have uv, so c psi m, minus the integral of v du. So c integral psi m prime dx. And this is really interesting because if we carry out that integral now that's in the brackets, we're going to have something that cancels out. We're going to have c psi m minus c psi m, which cancel out, which means this left-hand side of the equation, which we determined was a number, is 0, which is a contradiction to our assumption then. So therefore, as energy increases, nodes have to increase as well. So in reality, if you had an En that was bigger than Em, psi n would probably go something like this in between. That's just a rough cartoon, but yeah, more energy means more nodes. All right.